right, our next speaker this afternoon is Desiree Harvell, who's joined us from CSU San Bernardino. Desiree has been working this summer with Abby, and she'll tell us about their project together, seeking hidden helium in type 1c supernovae.
Thank you, Gwen, for that wonderful introduction. I'm actually really excited to be here, and once again, Desiree Harvell, I work with Abigail, Polin, and I'm part of CalBridge. But yeah, so let's get started. So this is essentially what I'll be going over, is just some background and theory about how we classify type 1c and type 1b supernovae. Another thing is how we plan to discover or seek our hidden helium as well, and the results of what we got from that. So some background information. We first can start with core collapsed or enveloped stars, which is essentially how massive stars die. And when that happens, it's when they use up all their hydrogen and helium layers. So it produces a large supernova explosion, which is very relevant because type 1c and type 1b supernovae are actually derived from these stars. Oh yeah, so what's produced in these explosions is radioactive nickel, which is really interesting because this is essentially why we even get to see supernova explosions in the first place, because these kind of show up on the spectrum. So it's the decay from nickel to cobalt into iron, and that's essentially what powers the supernova because they produce the photons. So yeah, classifying type 1b and type 1c supernovae, right? So essentially, type 1b supernova explosions have helium in their spectrum, and type 1c do have no helium absorption features in their spectrum. And they both do not have hydrogen, and once again, they also are derived from stirp envelope stars. So interesting. Yeah, so what does the spectrum look like usually? So you can see here, a type 1b has a helium feature right there, and a type 1c does not have that helium feature. It's just completely blank. So, and also the change in energy as well. So this is just something to keep in mind because it's very important for the rest of the presentation as well. So yeah, the big question here is, why do we see helium in type 1b supernova explosions, but not in type 1c? So there's two scenarios. One is that it's a possibility that maybe the star used up all of the helium, so there's no more helium left. Or there's another scenario, which is B here, which is that there could be hidden helium or undetected helium there that's just not showing up on the spectrum. So we're going with the type B here, the hidden helium theory, and actually we can get into that on the next slide. And we believe this because stellar evolutionists have actually found that it's very difficult to remove that helium layer completely. So and with that, it's actually in a study that has shown that it's actually possible that there could be helium there that's just going undetected that won't show up on the spectrum. So we've believed that if we kind of could confirm or deny this helium theory here, it could probably help stellar evolutionists have a better understanding of the stellar life cycle and how stars die. So yeah, let's get into the methods of how we plan to confirm or deny this theory here. So we're going to start with a ejecta model with helium on the surface. So this would be synonymous with a type 1b supernova explosion. And what we plan to do is adjust the nickel distribution, so the radial nickel distribution, while maintaining the original mass. So we don't want to change anything but the distribution of nickel here. And we do this because nickel is essentially the main source of photons. So we want to make sure that there's a little more overlap here. Another thing is what we're going to do is take that adjusted model and input that into the Sedona code, which is a radio transport program, which I will then get into later. And then from Sedona, it produces like synthetic spectrums. So we plan to compare those to the original and see if we can see any changes in terms of the helium feature. So our goals here are to test our hypothesis, which is that a centralized radial nickel distribution would produce weaker or diminished helium absorption features. We also want to confirm that our original model that has helium on the surface is actually synonymous with the type 1b model as well, just to make sure. So these are our two models that we have. So this is the original ejecta model with its original nickel distribution as well. So this model is about 4.5 solar masses, and we have here is just that the mass kind of expands radially. So this goes by mass accumulated radially, and the mass fraction is just what we're using to maintain a distribution, but keeping the original mass. So we're shifting it, and the adjusted model has the shifted nickel distribution here. So everything else is distributed accordingly to this distribution change as well. So this was generated with the MESA stellar evolution code, which then gave us our really neat ejected model that we're trying to change here. So this is all going into Sedona, which is a radio transport code program. And what it does essentially is kind of simulate photons being absorbed by the various elements that would be here. And this would produce a synthetic spectra or spectrum of each of those models that we have previously shown. So what is what is the typical type 1b and 1c spectrum look like? So this is what we are hoping our original model is synonymous with. It has that helium absorption feature. And this is what we're striving for with the adjusted models. So we kind of want to completely diminish that helium feature by adjusting the radial distribution of nickel. So that is our big goal, essentially. So let's see our results when we put it in and get our synthetic spectrums. So we do have confirmation that the original model is actually synonymous with a type 1b supernova explosion, because it has that helium absorption feature, and it is very similar to what we saw previously on that example as well. So it looks pretty much like a type 1b explosion, so which is awesome. Secondly, this is our adjusted model that we have. This is just the factor that we use for changing up the distribution. So it's squished like what we saw in the original two models. We actually have seen that there's weaker absorption features when we move over the radial distribution of nickel, which is actually really exciting to hear, because that's essentially what we were trying to strive for. So, So yeah, we have that weaker absorption feature of helium. And actually, we kind of observed that it got hotter as well, which is kind of unexpected. But it did look a bit hotter in the example as well. So really interesting. This is another distribution where it's kind of crunched by this much, so even more so. We actually found that the helium absorption features actually disappear, which is crazy. We were striving for that the whole entire time, and it's actually a really exciting result. And we also saw that it got even hotter right here. So that's something we're still trying to figure out why, changing that distribution made it hotter, but really awesome, honestly. Yeah, so to conclude, we actually were able to produce diminished or non-existent helium absorption features after shifting the nickel distribution. So really exciting result there. And the next steps would be to try more distributions, like more new distributions of nickel, and also try to understand why the temperature change occurred with each distribution change. So as it got more scrunched and squished, the temperature got hotter. So we're still trying to figure that out. But yeah, so it's just the references here, and thank you.
All right, questions for Desiree?
Thank you. That's a really great talk. It's really clear. I'm going to ask, it's not meant to be a hard question, but just sort of something you might have some intuition about.
Yeah.
If changing the radial distribution has this kind of impact, and I know the models can get very complicated when you're not doing spherically symmetric models, but if there were rotation and different mixing that happened because you broke that symmetry that wasn't spherically symmetric, would that have an impact, do you think, at a level that you're looking at? Just speculate.
Oh, so are you saying that it might be essentially how we scrunched it might have had an effect on why it got hotter? Is that what you're saying?
But also the way to have the helium go invisible because you're seeing it in different directions.
Oh, yeah.
And so all of those things may matter, some of them may not matter. curious if we have
Yeah.
some random thought.
Oh no, that's actually a really good question, actually. Like how we view helium might have an effect on how many things we get to see. Um, I'm not entirely sure about that completely, but we do believe that it might be just a lack of like stimulation from the radioactive nickel photons getting absorbed with helium. So I'm not entirely sure if it has to do with like viewpoint, but that's a really good thing to take in consideration. But yeah, really good question. Thank you.
Other questions?
So kind of similarly, I wanted to know, so even though in your observations you saw that it was hotter than you expected,
Yeah.
so can you maybe give us a reason why you think it would be, why you like hypothesize the temperature to be cold in the first place?
Oh yeah. I'm not entirely sure. I guess we found that it just got hot, unexpectedly hotter than it was supposed to be. Because I know that type 1C are usually a bit more energetic, but it's just wildly energetic than what we expected. So yeah, really good question. Thank you though. I'll actually ask my mentor about that too.
Yeah, a bit of a follow-up from that question. Can you kind of like explain and walk us through the graph and talk about like how the graph shows that it got hotter?
Oh yeah. Oh, oopsies. Yeah, so this is the original model here. So this is at, the flux is about 10 to the minus 4. Here we saw with our adjusted model, when we changed the radial distribution of nickel, it went a bit more above 10 to the minus 3. So it's about between those two. But I believe this might be also on a log scale as well. And this time it's like all the way towards a little bit above 10 to the minus 2. So the flux was increased, so it got a lot hotter. So very interesting observation. Yeah, very good questions. Thank you.
All right, we should move on. Let's thank Desiree.